Yes. Protocol armor, network of validators, and underscore G, blah, blah, blah.
Yeah, exactly. Vlad, did you get a chance to look at these?
Yeah, I did.
Okay.
I have a few questions about your notation, but I'm sure we'll get into it.
Yeah, that was why I wanted to put them together. All right, well, I don't mind recapping for Rick, or if he wants to look at the video later.
Just to look at this quickly, so we have a network, and I presume N and V are nodes and vertices, or rather, not nodes and vertices are the same thing. What are N and V?
No, N and V are just channels. So just to set the framework here, Vlad had this idea of what he was calling protocol armor, which can be thought of as a kind of a minimal skeleton or a skeletal framework in which to look at the various kinds of attacks so they can all be characterized. So what I did was to write down everything that I heard him say to verify that I got the ideas, so that we could then discuss whether or not that does in fact classify all the possible attacks within the framework. So that was essentially what I was trying to do, was to characterize everything that I heard, and then we could go back and see if I got everything correct, and then check and see if that does in fact collect all the attacks. Is that accurate so far, Vlad?
Almost. So the main kind of like place where we're like naming things differently is like I'm calling this the kind of like fault model, or the faulty computational model. Okay. And the protocol armor is the thing that is protocol armor is something that like you can add to a protocol in order to observe Byzantine behavior.
Got it. Okay.
But what we're really talking about now is basically the like all faulty executions of a protocol.
Right. Yeah. Okay.
All the ways that things could go wrong. And basically the protocol armor, what it does is it just really reduces the space of things that can go wrong.
Yep.
Yeah. And well, I mean, so I mean that's not necessarily true. What it lets you do is observe Byzantine faults from their observable consequences, whereas the fault model shows Byzantine faults from their behavior. So the fault model is more like the code that is faulty, whereas the protocol armor is something which lets you check whether messages coming in are coming from faulty nodes. So the protocol armor, I started off with the protocol armor to basically try to like see what's the most possible information about Byzantine faults that I could infer from an arbitrary protocol. And then I decided to look at faults from a more behavioral kind of point of view. Mm-hmm. And I basically found there's basically like four basic types of faults. And the goal is basically to have kind of a complete characterization of like all possible faulty executions, so that we don't need to have a definition of Byzantine that is doesn't lend itself to analysis.
Right. Exactly. So then to make that crisp, mathematically crisp within the framework of the pi calculus, what we have is a network of validators, which is parametric in channels N and V. Boldface is frequently used for vectors of channels in the literature. So that's what I did here, since it was a hell of a lot easier than doing the arrow. arrow overhead. So basically, we just got N, which is some index collection of channels, and V, which is some index collection of channels that are the parameters of N sub V. And that is defined in terms of a big parallel composition of some validators which have been stuffed into contexts and that is in parallel with an N sub C. And then we note that the N sub V and the N sub C are essentially connected by gates, which are in the context. So the gates are what either allow or prevent messages that are out on the N sub C to reach the V sub I's. So to make this a little bit more graphical, you can depict it like this. So essentially a validator V sub I might talk to a validator, V sub 1 might talk to a validator V sub 2, and it's essentially using N sub C as a communication substrate in which to do that. So it would normally send stuff this way, but there are these gates that are sitting in between both validators, which are making decisions or providing some mechanism by which to model certain kinds of messages making it through or not making it through or suddenly appearing, that sort of thing. Does that characterize what we were talking about on Friday?
Yeah. So on the main thing that I would like to point out basically is how this maps onto some of the types of Byzantine faults that I was talking about.
Go for it.
So basically, there are basically four types of faults. There's invalid protocol messages, failure to send a protocol message, and omitting a protocol message even though you received it. And then the fourth kind of fault is equivocation. And then there's actually one more, which is the network fault, which is not really a node fault. It's like a network fault, and kind of different types. So basically, the gates they model faulty behavior in terms of failure to send and censorship, i.e., omission of messages. Mm-hmm. So basically, if the network might route this message to V2, the V2's Byzantine gate here might say, no, I'd rather not, feed that into my betting function. So the gates basically will model failure and failure to send, so crash failure, and also omission. So after you receive something, not pretending you didn't. And the reason why this is kind of cool is because, normally, if we look just at protocol states, we can't tell the difference between failure to send and omission once the message was received. But we do often make that distinction, and so it's nice to have a model that kind of will basically let you basically evolve the protocol in whatever way, and you'll be able to get the same protocol state via these two different paths of faults. So that was kind of explaining the gates. The gates do the I/O. They kind of do the I/O faults, which are like omission and failure. The equivocation fault basically is basically going to be done in the validator, where the validators have to have a strategy for when what they produce bets out of their views, but their views are kind of given by G here.
So essentially what you're saying, to reflect back, is that we can think of every validator, whether they're correct or Byzantine, as a decomposition in terms of two behaviors: a correct behavior and some Byzantine component. And if it's all hunky-dory, then this thing is effectively a wire. It's a pass-through. and if it's more Byzantine, then this thing has additional behavior. Is that a fair thing to say?
So basically, there's a few there's a few options, right? We can. It depends on whether or not we put the strategy of the validator for when they decide to publish things and like when to make bets inside VI or inside GI.
Mm-hmm.
So if we put the decisions of when to publish bets in VI, then you can have the choice to equivocate will be done in VI. If the decision of when to produce bets is given by GI, then GI can do that, but GI needs to basically it basically will manage the view of VI. So basically, it will like have a store of all the bets it's received and all the bets that VI has given it, right?
Mm-hmm.
So there's a couple ways to break that down, but basically, what equivocation amounts to is, just producing bets in a particular way where you're no longer kind of single-threaded in the sense that any of your bets claim to see all the previous bets you've made, but you'll be kind of making different bets in parallel. So the behavioral definition of equivocation that I'm going for at the moment is having multiple copies of protocol programs and running them in parallel and being selective about which and how and basically like having and then the gate basically will act as a switch between all of these different copies of protocol programs.
So what we're saying then to reflect that back in terms of our picture and our math, that would look like if I take one of these things like that. Oh, come on, don't do that. But not that one. Okay, there we go. And then we get rid of this. Get rid of these guys. So what we're really saying is inside this box here. So from the point of view of the network, this is the validator here, right? So all these guys think that this is the validator, but in fact the gate is either contributing or hindering. And then what we're saying is inside that box, it may be even more like. It may be even more like something like this, where we've got.
That's right. So it's either like that, or V is actually made up of or V has more structure, and we can model the structure in there.
Right,
So
but
those three validators connecting to one gate represent
equivocation. So basically, for example, like an equivocating validator and realistic attack, what they would do is they would have a different version of Casper that they're running for each other validator in order to show them the thing that the best thing that they would.
By a different version of Casper, you mean a different strategy?
That's right. I mean a different validator node.
Right. Okay. So basically, you like the validator would like have three VMs, and the VMs would each have different strategies, and they'd all be fed the same information, but they'd react differently.
No, so that they would be fed different information, in order to conduct the attack.
Wait, but isn't
so that like some of the validators will believe that this is the consensus, and some of them might believe it's something else,
Right. But what about the kind of equivocation where like you could potentially react in two different ways and use react in both ways?
So that I think what I'm saying is that can be modeled as a copy of a program.
model as a copy of a program, and then like which choice you make would just be sort of part of your internal state.
That's right, exactly.
Okay, so if I understand,
so basically the idea is that my kind of dream here is to say that equivocation is making copies of protocol programs and running them in parallel and being selective about like which one you do IO with which party in the protocol.
Right.
Now this is only there's subtle issues about whether this is the case. It has to do with the extent to which you can check that the output of these of a something that produces protocol message really comes from the protocol. So if you have like 100% ability to check protocol message validity, then I believe my claim. If I don't have 100% ability to check protocol validity, validity of protocol messages, then it becomes slightly more subtle. Where instead of having just copies of the protocol program, we have copies. We just have a bunch of programs running in parallel, each of which satisfy the verification in terms of validity of protocol messages.
yes, yeah. So along those lines, then what you can say is that sort of an innocent validator looks essentially like a switch over function, right? So I've written down that shape as well. Hang on, I'm not sure what's going on here. Sorry, it looks like a typo. Okay, so an innocent validator has the form select over, so for each of the different VI channels that it's connected to, there's a case, and then within inside that, so one of these gets to fire. For single threadedness, right? This has to be a big case over one of the channels, and then you dispatch over the shape of the message that you've got, right? And then since messages within this sort of idealized framework only decompose into a sender, an estimate, and a justification, then what your dispatch is over is a specification that's a specification of the sender, a specification of the estimate, and a specification of the justification. And then depending upon which case you got, you will then do a broadcast back out to the VJs, in other words, all the other VIs in the parallel composition, with a new address being the address of VI and a new estimate constructed from there, and then the new justification. That's the innocent validator shape. Does that make sense?
I don't quite understand this this like match case sender composition thing actually.
So this is
Did anyone else understand? Maybe someone can give a.
It's just pattern matching, right? In Scala, right? So if you have some data structure, then the match case construct says is going to dispatch depending upon the first pattern that B can be used to pattern match against. So this is a common kind of linguistic construct in languages like ML, OCaml, Haskell, Scala. All you're doing is checking to see if this data structure, the instance of the data type that BI is, matches against some particular shape, right? So here we know that B.
I have a question.
Yeah, go ahead.
So what is a non-innocent validator doing that doesn't fit into the pattern matching structure?
So a non-innocent validator, for example, in the case of Vlad's dream of how to characterize equivocation, a non-innocent validator would have, instead of a select here, would have potentially a parallel composition, right? So not just a select, but it would be run. So for example, it might take the V space here and bifurcate it into one range where it's doing one set of calculations and another range where it's doing another set of calculations.
Okay.
Yeah. So so are you putting together a new bet here?
Right, exactly. So I've also tried to use the picture down here to clarify this code, right? So in the case that the BI is of the shape SEJ, where S is inside sender spec, E is inside estimate spec, and J is inside justification spec. That's when you'll go here, and what you do, well, what you're broadcasting out to the VJs. So this is a send, right? If this is a receive, this is a send, and you're to each VJ, and you're going to send out the message where the new message, which is another triple, right? The address of which is coming from here. The new estimate is calculated by the new estimate of this guy, the new estimate function of this guy, and the justification at a minimum includes the bet we just saw.
Okay, and realistically, it might include something else, and there needs to be logic in the validator for what else it includes, right?
Exactly right.
And a Byzantine validator might have, say, a logic that says, I'm going to include, different things for a different copy of the for a different picture for every other validator.
That's correct, and that's what I was saying before. Is what we're trying to characterize is the innocent validator, so that we can test or probe this idea that you can decompose all Byzantine behavior into go back to the picture here, innocence plus a gate, right? Innocence running in parallel with a gate, right? And in fact,
I think again, there's two ways to break it down. Yeah, that's one way. I'm not sure if that's as I think we're going to have to add a little more structure into V in order to say how V decides when to make bets. And then I think this would be like pretty complete.
Okay. All right.
So basically, and then the last type of fault that we haven't really mentioned yet is the network fault, which basically has to do with the network's ability to choose the order of message arrival and to stop message arrival. So you can just decide, I'm never going to send this message, or they'll send it after they send an infinite number of messages first. So so basically the idea is that all that this like all possible reductions of this program will be all possible faulty executions of the protocol. And so and the reason why it's kind of cool is because the method that we did to get here is somewhat general, and then the main thing that isn't super general and that determines whether or not we're going to actually be able to do this whole fully typing and describing all faulty executions is whether or not we can actually verify protocol messages in order to restrict the program that they might be running to something that basically does something deterministic and can be checked, or something that maybe will produce a proof in a way that can, or anyways, something that can be really, really checked.
Yeah. So then what I want to do, let's go back to this picture and observe that there are, in fact, two ways we can talk about the validity of the protocol message. And that falls out from the spec. So we can talk about the shape here, right? So you could imagine that a compiler can do case exhaustive analysis. In other words, does the set of cases over which you're doing analysis of the message, does it exhaustively cover the space? Or are there some types of structure which would not be covered by the cases. And all of that leads into validity of the message that has to do entirely with respect to the shape of the message itself. So for an example, an invalid message shape. So if all messages are triples, right? Where you have a sender spec, or where you have a sender, an estimate, and a justification, if that's the triple, then an invalid shape would be maybe swapping the estimate and the sender in the order of the triple, right? That's an invalid message and might occur when you have a network failure that tears apart these things into packets and then reassembles them incorrectly, or might occur if you have some bug in some validator code somewhere, which you can't tell from.
We're going to protect against the network thing with like signatures and hashes, right?
Yeah, of course. I'm trying to be illustrative, not necessarily say that that's what would happen, right? But there are lots of ways in which things could go wrong. For example, the justification spec might be instead of being a set, it might be some other kind of shape.
So we all kind of understand like malformed messages.
Cool. All right. So, but malformedness is not just that they're ill-formed, right? They might.
They don't pass some self-authenticating check. So basically, we're saying there's like some extent to which validity is self-authenticating. There's like to which you can just like look at the data structure and like run a few functions and say, okay, yes, it's cool.
Right, exactly. And then there's a second set of validity checks that have to do with, even though the message has the right shape, it's arriving at the wrong time in the state of the protocol. A standard example would be like in a simple protocol where you have an initialize session, do some work, finalize session, which is typical of database connections as well as other kinds of things. If you send a do some work before you sent the initialize session, that would be arriving at the wrong state in the protocol. And that's another kind of challenge to validity that we would we want to be able to characterize, but that's much more subtle than the message shape kind of thing.
Right. Exactly. Right. And so this is gonna limit our ability to describe all faulty behaviors, because like the bigger the space of things that seem valid, the more that we have to take the definition of Byzantine behavior to be, untyped.
Right.
So I'm a little concerned that we are getting a little bit too deep, and we haven't given kind of like a chance to talk.
Yeah, absolutely. I just
want to quickly wrap up. Maybe you have any last. Sorry, you know.
All good here. I just wanted to make sure that we talked through this and you felt that I had accurately reflected an understanding of our discussion.
Yeah, I think the main question for clarification is basically around the logic of what is deciding, when to produce new bets. Is that in G or is that in V, right? And it's gonna like affect your picture on Canvas 5 in some way, and maybe. I mean, you might be able to add more detail.
I could. Yeah, sure, absolutely.
Okay. So I think that's the main thing. But basically, I just hope that it's like clear that what we're doing here is like describing all the faulty behaviors and basically like and looking at all the faulty executions of the program. So, the idea is that like if these VIs could be just general programs in a protocol, and like each of them could have a gate and a network, and these gates and network things are quite general, and they basically just get to make arbitrary choices by default, and then you can restrict them if you want to look at only a subset the faulty executions.
Right. So as I understand it, then you're thinking about that from the point of view of being able to situate Casper relative to other kinds of protocols in the literature like BFT and so on. So if you make this general enough, you can instantiate this, you can specialize the framework and arrive at BFT. Or
At least at a determination about faulty executions, right? To have Byzantine fault tolerance, you actually may need protocol changes. But the idea here is just to like look at faulty executions, and if you have fault tolerance, then basically there's going to be like more paths of faulty execution that where some protocol guarantee holds.
Wait, but hold on. But isn't the whole point of like protocol armor to try and turn any protocol into a BFT protocol, or am I misunderstanding?
No. It's just. I mean, eventually, I mean that's a kind of a long-term goal. At first, it's just to observe Byzantine faults, and then to determine whether or not guarantees hold under a certain Byzantine fault assumption, and then so basically it's for observing faults and determining fault tolerance of a protocol.
Mm-hmm.
And I'm hoping also to find a way to make any protocol into a Byzantine fault tolerant protocol. However, that's actually a much higher ask because a lot of protocols move into undefined territory due to Byzantine behavior. But what I feel more comfortable with is just run the protocol on top of consensus protocols and make every process in the protocol replicated. Now we have fault tolerance, right?
Right.
Although it's
simple.
not necessarily the fault tolerance in the sense that any process in the protocol can fail. It's that the process in the protocol are made up of things that can fail.
There is one concern is that what if these processes are supposed to contain private information?
Absolutely. Yeah. So that is absolutely the concern, right? And that's a concern not only for the make any protocol BFT by running it through consensus. It's a concern also just for the armor, which lets you observe faults because it may just the information required to check protocol message validity, for example, might leak information, right? Or there might be the fact that every message has to point to like the previous message sent by that node in order to detect equivocation may leak information.
Right, I see.
And so, as soon as we start talking about privacy, a lot of this stuff becomes trickier because it's basically an additional constraint, right?
Right.
And basically, and we need some kind of information we need to look at stuff in order to tell whether we're looking at Byzantine faulty behavior.
Right. So the other kind of armor that might be worth looking at is basically like, could there be some way to automatically figure out what the right economic incentivizations are to like make any protocol sort of incentive compatible?
Right. Yeah. So that's totally right. And basically the way that I'm hoping to do that is to say, oh, look, there is this faulty protocol state.
Mm-hmm.
And I might have gotten here through this sequence of faults or that sequence of faults, right? It could have been a network fault, or it could have been this guy's gate, or it could have been that guy's gate.
And then you isolate a subset of people that might be responsible, and then you punish them.
Exactly.
And potentially you use like some like Shapley thing if you want to like do weighted punishments, and you like have some information about what coalitions it might be.
Shapley? What's Shapley?
Shapley values, like from cooperative game theory. I just, some reason I get the intuition that stuff might be relevant.
Okay.
Okay. Right. So like one thing that would be nice, right, is if we could automatically make incentivized PBFT or like incentivized Dominic Williams consensus or whatever.
Yeah, so that is kind of one of the goals, right? And that's why I'm starting with the protocol that I want to tell if it's BFT, and then like kind of doing it rather than and it's kind of like the approach here is like first you find what you think is like the solution to the the thing that you basically are, the more you can specify what you want to incentivize, you're the easier it is. The more what you want to incentivize is, something that looks like Y, but you don't really tell them how to get to Y, or there's like a big possible set of possible protocol accepted programs that you can run.
Right.
Then it's much more challenging.
Right. So, like, the way I tend to view this sort of stuff is that you want to incentivize actions that try to bring a system toward consensus and disincentivize actions that look like they're moving you away from consensus.
Yeah, I agree, but I don't see, so that type of thing seems like much harder to do, to provide a mechanized process for
Right.
generating the incentives.
So, like, one way that I might see for mechanizing it is if you imagine making a graph of all possible protocol states where some of them are finalized, then you could try to figure out what the distance is of some state from a finalized state, and then try and reward things that reduce the distance. Like, that's theoretically executable.
Yeah, that sounds good, but then you actually have to give these protocol states. Yeah, you have to basically give the protocol states and say which ones are preferable, or
right.
which I guess is different than what I was suggesting earlier, which is to
just look at
protocol behavior, give the actual node strategies.
Oh, right, I see.
So, and I want to argue, or at least inform, one of the principal motivations of the movement away from the graph-based approach to the process calculi approach was precisely the complexity issue. So when you write P par Q, the graph of states that entails is ginormous potentially, right? It's quite large. It has to do with all the interactions between P and Q. But if you just write it as P par Q, you get this enormous compression. And so if you have to unfold the graph, then it quickly becomes super unwieldy. And this is, in fact, one of the reasons why I started vigorously investigating the process calculi, because we were doing these kind of relaxed transaction style dependency calculations using graphs. And we found that with 3 nested dependencies, we were just completely overwhelming the best hardware at the time. Whereas with the process calculi, we could safely do orders of magnitude larger calculations. So that's the kind of if we can get it into this more behavior based or to introduce the language that I was using with Vlad on Friday, intentional specifications where we're talking intention with an S, not a T. Then you have a much better chance of managing the complexity. Again, just a little bit of data from the literature. If you're looking at language equivalence problems where you don't have any intentional structure, just language equivalence for regular expressions is p-space complete. The corresponding bisimulation problem is polynomial. Language equivalence for context-free, you can't do it, not decidable, cannot be done. Language equivalent, the corresponding bisimulation problem, polynomial, right? So you go from can't do it to can do it in polynomial time if you include the intentional information.
Okay, well, so kind of let's try to make this relevant to our context a little more directly. The idea is basically that we kind of have a choice, and I mean I think we kind of need to be doing both in different contexts, but between looking at behaviors of nodes and possible protocol states, right? And should we be incentivizing protocol states, or should we be incentivizing behaviors of nodes? And I think the answer is, we should be incentivizing a behavior of node by using evidence that can be basically by using kind of information about which behaviors could have led to a protocol state.
Right.
And so I think we need to talk about both and if you are incentivizing a behavior, I think it's easier to mechanize. I think it'll be easier to mechanize the incentives than to incentivize protocol state, because the behavior basically corresponds to a program already. It's already like a process in some way.
Right.
Say like, but then the main kind of question again is, to what extent can you really verify that the program is really running the right thing? And the idea the idea is that what we want is for like putting blocks together to be deterministic and checkable, right? And then basically the only other question is, about kind of like mempool and block management to kind of like decide like where to put your block and what transactions to put in it.
Well, I mean, alternatively, I mean, or not even alternatively, but in concert with that, you can have notions of chains of custody, right? So if you have a verification of a particular protocol implementation, some expression that looks like this, and you have a formal proof that it is correct according to the published spec, right? And then if you have a chain of custody from the code to all the way out to some execution environment that you, with some confidence, believes is okay or trustworthy, then again you can have you can utilize verification against the structure of the program to guarantee all kinds of safety and liveness, right? In a trustworthy setting. It's only in those cases where you don't have chain of custody that you have to protect against in a more draconian or so something that's a lot harder to do. Right. So that's the trade-off, right? Is essentially chain of custody to the trustworthy execution environment versus not being able to say very much about the execution.
Well, I mean, but the idea with like self-authenticating messages is that like or like blockchains and like certain like these kind of cryptographic protocols all the time is that like we try to bake as much auditing as possible into these messages, and so actually you end up being able to say quite a lot.
Yeah, you can say some, but you really can't say stuff about the state of the protocol, right? So validity is still very elusive without being able to say something about the state of the protocol and the
So I mean that's right, although so it depends on the type of validity, and we really do try to minimize the amount that we rely on like subjective validity, right? Like we don't like to introduce subjective validity unless really necessary. And so basically what I would like in the end, for a protocol that like lends itself to fault tolerance analysis, I would say we should be able to model it as a bunch of functions that a process that decides what to feed into some fixed set of functions. Basically, these kind of gates that manage I/O with deterministic functions. I think that's basically as good as it gets, because I don't think that we'll ever be able to verify, that you omitted a message versus, that it wasn't sent, because like absence doesn't. Yeah. So basically, I think cryptographers and like crypto, we really try hard to move towards a place where we can tell as much as possible, or authenticate as much as possible, or at least as much as necessary about what some process on the other side of some Byzantine gates is doing.
Cool.
Great. Okay.
Any other updates from folks? We got about 7 minutes left in the hour.
Let's see. On my side, I've been working on a scalability, or rather, it's a sharding FAQ. I think I already pasted it in a bunch of the rooms, so it's in there. Also thinking, I'm starting to think, and I want to like think through it with a lot of other people, like just in the simple case of like minimal, sort of no finality, just like longest chain style Casper, and see if we can figure out what the incentives can be for the thing to be incentive compatible even under majority collusions.
Cool. Yeah, that's actually really attractive to me. I've been thinking about subjective finality and basically the kind of trade-offs that are involved there. The nice thing about subjective finality is that the protocol is nicer. It seems to be like much cleaner.
What do you mean by subjective finality here?
Everyone chooses their own finality threshold.
Oh, I see. Right. So like, right.
So like, so basically, it's the finality threshold that you choose is basically your level of comfort / trade-off between
Right.
optimization and consensus failure.
Right.
So if you choose to store everything, then except for like a very like potentially unlikely case of unanimous consensus, you won't have finality because like you've decided that like 100% is what you need.
Right.
But you'll you'll kind of always be on the quote unquote longest chain. But if someone else decides like they're going to do 50%, then as long as there's not more than 50% equivocations, then they're going to end up being on the same chain as the guy who said 100%.
Right.
And they'll have to store much less overhead. They'll be able to do lower, because they don't need to revert as much. It's just kind of a lighter protocol for them, right?
Right. Yeah, I mean, like I tend to view that stuff as being client strategy.
Yeah, that is client strategy. Yeah, and then the main kind of question. So the main place where I actually do seem to need there's two places where I do seem to need finality and protocol, at least to some extent. So which are validator rotation is one of them, and the other is incentivization, right? So I want to incentivize the production of safety. I'm thinking that I'll be able to do that even with a subjective finality threshold because I'll just, if you can show that you provide some amount of safety, then I'll you get paid for that. And if you provide more, you get paid more. It's not a binary question of whether you've provided this threshold amount. But with validator rotation, I think it's a bit trickier.
So, like in my case, the places where I realize that you might need to have hard thresholds are. So one of them is that you do need to limit how quickly validators can converge, or like you need to specify you can't let people just like immediately bet finality because that would make the whole value at loss thing exploitable.
Yeah, I agree.
The second thing is that you need to I care about bounding griefing factors, and that's in general, the more sort of conservative your rules are, the better the griefing factors are.
Sorry, I didn't quite catch that. Want to tell me more? How is that a threshold thing?
So basically, the idea is that if you have a threshold of, let's say, 51%, then potentially an attacker could use a fairly small amount of stake on start one shard or start one path, and then then take the rest of their stake on another path, and they don't really equivocate that much. Like their equivocation is basically 1%. And that's but so the griefing factor is potentially high because fairly small losses could cause you to lose a lot of money. Or
right. But there's no in-protocol threshold there exactly. There's just like kind of a in-protocol gradient of how much money you look at different thresholds.
No, the threshold there is 51%, right?
Oh, I see what you mean. It's a kind. I mean,
if you change the 51 to like 95, then on the other extreme, you're like very griefing resistant.
Sorry, I you kind of spoke really quietly there.
I said if you change the 51 to a 95, suddenly you're extremely griefing resistant. So why is 51% the griefing threshold? I don't really. No. If you 51% is a threshold for the finality thing to escalate, then you need that, right?
Then you need what?
Then, like, basically the attacker only needs to equivocate with 1% of their.
I see. Yeah. Right. So yeah, and I mean this, and I used to kind of have this approach where I basically would require some threshold in order to allow your bet to be for you to put more than certain value at loss. But now what I'm doing is quite different, and so I don't have this threshold anymore. Basically, because you don't actually have a value at loss in my kind of crack back constructing Casper. It's just the only value at loss is. I mean, there's going to be some value at loss when we talk about like incentivizing liveness, but in terms of safety, it's just about like kind of calculating whether or not the estimate can change given a particular equivocation context.
Well, in general, you're going to be sending messages, and there are going to be contexts in which like some messages cause you to lose money, right? So like value at loss as a concept is pretty inevitable.
That's right, but I just don't have like some idea that like only if you see some threshold of messages from a stake can you know.
Right, I see. Yeah, like.
Okay, so there's basically a threshold for when you allow people to ramp up their value loss.
Yeah.
And that's like an in protocol threshold.
Mm-hmm.
And basically like you're thinking like 2/3, like 51%. What are you thinking?
2/3, 3/4.
Okay.
2/3, but the griefing factor argument maybe wants to go slightly higher.
Okay, so how does this relate to your like, oh, how are we gonna do Casper without the finality cycle?
No. Like there's always a version of Casper without the finality cycle, right? It's like the simplest one. It just doesn't have as many nice properties because the cost of reverting n blocks is only O of n.
But I mean, aren't you still putting more and more of your deposit onto?
Well, no, because no, this is like very basic Casper without the more and more part, right?
Okay, so wait, there's right. So then the value at risk is only kind of this kind of like basic, like there's like it's like constant.
So just what I want to do is just make sure that at least that very simple protocol can be made to be kind of hardened against pretty much all forms of economic exploitability.
Right. Yeah. So yeah, in my world, like the kind of the hope is like similar, basic, but it's like I'll be able to have this kind of bet structure where I don't need to have finality be mentioned, but it's just something that you do as a calculation client side, and it's and like it would be like something that could potentially like reduce the overhead of the protocol, and basically then it kind of makes more explicit this idea that your the safety like that, like that you could choose your own fault tolerance kind of threshold for when you're willing to accept something as finalized. And one of the reasons why I think that's cool is because the kind of fault tolerance numbers that people normally give have to do with the fact that they can't actually have a fault tolerance that's so high that if that many nodes were faulty, then the protocol wouldn't have liveness, right? And so that's why like a third is the upper bound. But I think in practice, what will happen in terms of reversions is that the protocol will be live while it does something that it wants you to think it's doing, and then it'll go and revert it, right? And so the Byzantine fault that we're worried about is kind of liveness followed by equivocation, which is in kind of a different world than this world where like we can only have at most a third, because if we have more than the third, then we don't get to have a Byzantine quorum because a third will go offline. Whereas what's really going to happen is like we can have a very large Byzantine quorum, and a very large number of them will equivocate in order to switch. Because if you don't have a very large Byzantine quorum, then people aren't going to spend.
No, this is really nice, and this is the kind of thing that needs to be documented, because I think a lot of people who work in this space are unaware of these possibilities arising in this new context. So that's the kind of thing that I'm very excited about. But on that note, it's 8:05. I do have to jump off, and I will hopefully chat with you guys next week.
Hey,
when is everyone coming in, by the way, for those who are going to Singapore?
I'm either going to be arriving Wednesday morning or Thursday morning.
What's happening in Singapore?
Flight yet?
No, I haven't booked my flight yet.
What's the Singapore event?
It's not an event. We're just hanging out. If you want to come, I mean, I'm flying Singapore in a few days until like December 3rd, 4th, or something like that.
I see.
Yeah.
I might hang out a little bit longer. I'm not sure what I'm doing afterwards.
By the way, I don't think you're going to be arriving Wednesday morning, because the flight to arrive Wednesday morning left 2 hours ago.
No, it leaves at 10:30 p.m.
Oh, right. Maybe I'm thinking in terms of. Okay, never mind. I kind of assumed that Singapore time was U.S. time.
All right, guys. Oh,
Okay.